Right. So as always, we begin by diagramming the problem. What are we being asked for? What information are we being given? In this case, we want to know which of the following is a possible set of quantum numbers for an electron. So the whole question is what we're being asked for. And the key here is that we're being asked for what's a possible set, right? Which one of these is okay, given the rules that we know for assigning electrons to orbitals. So, what we're being given then, in this case, is just some answer choices, and we have to decide which one of these does or does not violate the rules that we have. So let's think about those. We're given some information about our principal quantum number, we're given some information about our angular momentum, our magnetic quantum number, and the electron spin. One of these we can get rid of immediately by looking at electron spin, because we know for sure that we're not allowed to have a spin for an electron of 0. So let's just get rid of that one right away. The rest of them we can use the rules that we know about quantum numbers in order to decide what's real. So we know this. N is going to be equal to any positive integer. Right? By this we mean basically 1 to infinity. Any of those are okay. But once we've picked an n, then L is limited by that. L is going to be equal to 0 through n minus 1. So now we have our first criterion for deciding what's going on, right? We can't use n because any positive number is allowed. So B is not an answer because n is 0. That's not a possible choice. N has to be 1 or more. Moving on to L, what we find here is we need to find an L value that is somewhere from 0 to n minus 1. L is not allowed to be negative, and so we can rule out choice E as a result. And then L has to be less than n, and so both D and A are still okay. Then we look for ML. What are our rules for ML? Well, ML has to be equal to minus L through 0 to L, and it needs to be an integer. So let's have a look at what we got here. We're trying to decide between choices A and choices D. Here we can see in A that's an incorrect choice because ML is greater than the negative value of L. So that one's ruled out. This leaves us with D as our proper choice. We can check it real quick. We have n equals 3, that's okay. L equals 1, that is less than n, but still a positive integer, that's good. ML is minus 1, which is just minus L, so that's allowed. And then MS is plus 1/2, which is definitely a value that we're allowed to have for an electron spin. So D checks out as the right answer, and that'll be our right answer for this problem. Moving on to our next problem. Here we can have a look at what are we being asked for. Well, we're going to have some answer choices. We need to know which electron transition is the highest emission energy. And what we're being given are just some answer choices. Okay, so there's two ways to solve this problem. We could use the equation for the energy of a hydrogen atom, right? And then we could look at each one of these choices, plug in the values before and after, and come up with numerical values, rank those numerical values, and then select the correct problem. But it turns out we can do this entire problem without using an equation. How do we do that? Well, to begin with, we can get rid of a few answer choices by carefully reading what we're being asked for. And that's that we need the emission of a photon. What that means is if we have two different levels, right, we need to start at a level above one and go down. That's an emission process. We know that when we have this sort of transition, we're going to emit a photon. So anything that begins in a lower level and ends in a higher level would be absorption, not emission, and we can get rid of those. That's answer choice B and answer choice D. So already we've gotten rid of 3. All that's left is to decide, or gotten rid of 2, what's left is to decide between the 3 that are remaining. How I would think about this is as follows. Let's just start drawing energy levels. We can see that the highest energy level we need to consider anymore is 6, and the lowest one we need to consider is 1. So let's just draw 6 energy levels. There's 1, 2. I've drawn a spacing between those, but we know that the spacing between levels decreases as we increase the numbers. So the next one I'm going to draw a little bit closer together. That is 3, 4, 5, and 6. Great. Then I would just think about these electronic transitions. So let's think about A. A is going to be from level 6 to level 1. So here's 1, 2, 3, 4, 5, 6. And we want from 6 to 2, sorry, for A. Then we need to think about C. That's from 5 to 1. That's answer choice C. And then we need E, which is from 3 to 6. Oh, we could have eliminated that to begin with. 3 to 6 is an absorption process. That's clearly wrong. So we're trying to decide between A and C. When you look at this picture, because we've drawn these with decreasing spacings between the levels, it should be clear that C results in a larger difference between the 2 levels than A, and that that's a correct choice, even though the total energy change in both of those was 5 levels, right? In one we went from 5 to 1 and the other from 6 to 2, but because the biggest gap exists here for between levels 1 and 2, that's going to end up giving an overall larger energy difference. And so we see that we can solve this problem that appears at first to be quantitative by just qualitatively considering what we know about the energy spacing in a hydrogen atom. Our next problem is also sort of a qualitative or a conceptual question. We're being asked for which orbital has the quantum numbers n equals 4, L equals 2, and then we're being shown some answer choices that show us shapes of orbitals. And so if I'm solving this question, all I would do to make sure I don't make a mistake is write out what the quantum numbers are for each of these shapes. We know shapes have a given letter designation based off of their shape. For instance, answer choice 1 here, we would call this a p orbital. And we know that p orbitals are associated with L equals 1. Shape 2, that's a d orbital. That's L equals 2. Choice 3, this circle, that's an s orbital. We know that's L equals 0. Again, for choice 4, we have a d orbital. That's L equals 2. And then lastly, we have another d orbital. It's just turned by 90 degrees. This cloverleaf shape is a d orbital. And so we have L equals 2 here as well. And then all we need to do is circle those for which, let me erase this, L equals 2. We've solved our problem. We were given 2 bits of information up here, L equals 2 and n equals 4. But if you think about this, n equals 4 doesn't place any restriction on L equals 2, right? N equals 4, L has to be equal to 0, 1, 2, make that a 1, 2, 3. Okay, so we have 4 choices for L, 0, 1, 2, or 3. And 2 is one of those. So this n in this case, this was extra information that we didn't actually need, and we were just looking for values of L equals 2. And that's answer choices 2, 4, and 5. Our next problem also deals with energy levels in a 1-electron quantum system, And we're being asked for how many lines would there be in an emission line spectrum. Okay, there's a bunch of information given in here, something about it being a one-electron quantum system, but that's a little unnecessary. What we do need to know is that these are the only possible levels and that we're dealing with an emission spectrum. So we only want to consider transitions that start from the top somewhere above and end up somewhere down below. And then we're being asked how many lines would there be in the emission line spectrum. Okay, so if I were solving this problem, then I would just start methodically. Let's start with a transition from the top most level. We could go from the top all the way to the bottom, or the top to the second, or to the third, or to the fourth. Let me draw that right for a second. Fourth. Okay. So, from the topmost level, we have 4 transitions. We don't draw any arrows going up because that would be an absorption. So, let's consider the next level. We can start on the second highest level, and we can go down to the bottom, the second from the bottom, or the third from the bottom. Again, we don't worry about going up, because going up would be an absorption. This is 3 transitions. Okay, next level down. Oops, let me try to draw that. There we go. So, next level down, 1, 2 transitions. I think you can see the pattern here, but we'll go ahead and finish it up. And lastly, that's the last transition that we might observe. So here what we've done is we've exhaustively looked at how many transitions are possible from the highest, the second highest, the third highest, and then the least highest energy. We've accounted for all of them that are emissions. Those are arrows that are going downwards, and so we can just add those up. 4 plus 3 plus 2 plus 1, that equals 10. And so we have 10 lines that we would expect in our emission line spectrum. And so we begin our final problem for this set, again by looking at what we're being asked for. The frequency of a photon absorbed in the hydrogen atom, and we're given that the absorption is going to go from the n equal 2 level to the n equal 4 level. Good. So, how do we approach this problem? Well, finally we have to do a quantitative problem where we're going to use something we know about the energy of a transition for the hydrogen atom to figure out the frequency. And so the basic idea is this. We want to find out the energy of transition, and then we're going to use this to find the frequency of transition. We know something about the energy of transition. The energy is going to be equal to the Rydberg constant, 1 over our initial level squared, minus 1 over our final level squared. And then we also know, once we have the energy, something about how to relate the energy to the frequency, which is this. Energy is just equal to Planck's constant times the frequency of light. Which means that if we want to find the frequency, we just take the energy that we find and divide by Planck's constant. Good. So we're going to find the energy, and then we're going to plug it into this second equation over here. So let's do that. The energy. Well, the Rydberg constant is given to us, and you'll have it on your data sheet when you're taking a quiz or a test. It's 2.18 times 10 to the minus 18th joules. It's fairly small, but remember we're solving for the energy of a single photon, so it makes sense that it might be small. Then we need 1 over our initial level squared. Our initial level is just where we begin, so n equals 2. So that's going to be n equals 2, so 2 squared minus 1 over our final level squared. Our final level is just where we end up, n equals 4. So it's going to be 1 over 4 squared. Whoops. Good. Then we can run these numbers. What we'll find is that the energy of the photon is just going to be equal to 4.09 times 10 to the minus 19th joules. We're going to take this answer then, and we're going to go ahead and plug it into the equation we have for solving for the frequency. Let's go ahead and do that. We know that the frequency is just going to be equal to the energy of the photon divided by Planck's constant. We just solved for the energy, 4.09 times 10 to the minus 19th joules. We can put Planck's constant on the bottom, 6.63 times 10 to the minus 34th joules times seconds. Alright, let's take a second, as we always do when we have an equation with multiple units, to analyze our units. We're going to have our joules cancel out, and we're going to be left in terms of units of per second, which is the unit of frequency which we're trying to find. So that's fortunate for us. It looks like we've done our math correctly, and we just have to make sure that we type in the numbers right. When we do this, we find that we have 6.17 times 10 to the 14th per second. Per second is also sometimes called a hertz, so we might see this as 6.17 times 10 to the 14th hertz. But in this case, you can see our answer choices were actually given to us in terms of per second, so we're doing okay. Then we just have to find the one that agrees with the answer that we found, which is answer choice A, and we're done with this problem as well.